about star formation rates and star formation histories on fire.
Hello? Good. Good afternoon, everyone. First of all, I would like to thank the organizers for inviting me to the conference. This is my first time here, and it's really exciting to be here. And today I will be talking about my work on quantifying the star formation rate, rates in these indicators. So before I begin, I would like to give special shout outs to some of my mentors and collaborators. There's Claude Andre at Northwestern, along with his graduate student, Alex Gurvich. And then there's Martin Spar at Potsdam University, Christopher Hayward at the Center for Computational Astrophysics at New York, and of course, James Bullock. So in my work, I use the self-consistent star formation histories realized in the fire simulations in order to quantify the difference between observationally inferred star formation rates. And as here, what you see is one of the Milky Way-like simulated galaxies shown by Andrew Wetzel earlier throughout the week. And what about star formation rate indicators? Well, as we know, there are various ways to determine the star formation rate of a galaxy. One of them would be, for instance, observationally, astronomers could calculate the flux, say coming from H-alpha emissions, right? And with some assumptions and using a calibration constant, they could derive a star formation rate from that. And in order to visualize what it would see, this is the Milky Way as it would be seen through an H-alpha filter. And when astronomers assume a constant star formation rate, it is known that this indicator works at short timescales, which is about 10 million years or so, because most of these H-alpha emissions are coming from these ionized regions in these massive young stars who are dying fairly quickly. The similarly thing could be done when looking, say, at UV light, for instance. I'm interested in the FUV indicator, the far ultraviolet indicator. Similarly, it could be done, right, with assuming a constant star formation rate and using one of these calibration constants. FUV derived star formation rate is also derived. And here is again what observational astronomers would see, right? And what it would see in the optical, and then what it would be seen through a GALEX ultraviolet filter. And this indicator is known to work at longer timescales, which is about 100 million years or so, because most of the UV light is coming from these less massive stellar populations. And to summarize what I've said, here is one of the plots. So in the black here, hidden behind all these lines is a burst of star formation that has occurred in one of our simulations that has been normalized. So it increased the star formation by a factor of 10. And in the dotted blue, we see the response of the H-alpha indicator. And as you can see, it's better at probing the instantaneous star formation rate, right? It's working at shorter timescales, which is about 10 million years or so. And for FUV, it's about, which is the dotted red line, it's working at longer timescales, about 100 million years. And do not worry about this gray line here. It's just the ratio between the indicators, which is often used to determine whether the galaxy has gone a burst or not. And I'm not too interested in the ratio here. But traditionally, as I mentioned, H-alpha indicators work to known as short timescales, about 10 million years, and FUV about 100. And this is all assuming a constant star formation rate. So what do I do in my work? So as it has probably been mentioned, some of the star formation histories in the fire simulation tend to be quite bursty. For example, this is the star formation history of a Milky Way-like galaxy, and here we see that earlier in the universe it's quite bursty, and then it seems to settle down some later time. And what I can do is, using a stellar synthesis model, I could also derive the star formation rates using these H-alpha emissions and these FUV light. And I'm interested in quantifying the differences between these indicators and the true star formation rate in the simulations at these two regimes, which I call bursty, where the galaxy is experiencing these really bursty star formation rate. And then when it's somewhat settled down, non-bursty or more time steady at where the star formation rate has settled. So I generate plots like these. For example, in the first column here, we have the bursty regime. Second column is the non-bursty regime shown in the previous plot. The first row in the y-axis corresponds to the star formation rate derived by H-alpha emissions. The second row is in the y-axis derived by FUV, light. And in the x-axis on both of these columns is the true star formation rate. And for this particular plot, I have averaged it at a time scale of about 10 million years. The dotted line is a one-to-one line. The red line is a best fit line between the data, and it's color-coded by the redshift. So in plots like these, what I'm interested is in determining at what average time scale, when I average the true star formation rate, do I minimize the scatter between these two, the true star formation rate and that of the indicator in the y-axis. So in the next slide, you'll see a quick video of me averaging out the true star formation rate at 1 million years, 2 million years, and so on. And we notice that at some time scale, we have a more one-to-one correlation, which would indicate that the true star formation rate is mimicking that of the indicator. So here it goes. We saw it somewhat minimized, and I know that was fairly quick, so I'll replay this one more time. Right around 4 million years or so, we see that the H-alpha indicator was the scatter between the data points has minimized. And for FUV, it's maybe a bit more harder to tell, but it's roughly about 10 million years or so that I'm seeing this minimized scatter between these two. And to summarize that better, here's at 4 million years or so, we see that we have a more one-to-one correlation between these two. And FUV was about 10 million years or so. So I've done this for multiple simulations. So each color represents a different simulation, all varying in mass, where the black one would be a dwarf galaxy, the blue one is an intermediate dwarf, and then the magenta one is the Milky Way-like galaxy. The solid line corresponds to the bursty regime. Dashed line corresponds to the non-bursty regime. And notice in the y-axis, I have the normalized scatter between the data set shown in the previous plot, and then in the y-axis is the different average time scales in which I average the true star formation rate. And we see that for H-alpha, around 4 million years to 5, we notice the minimum scatter, meaning that the true star formation rate is mimicking that of the indicator. And for FUV, it's, again, not so subtle, but it seems to be happening around 10 to 15 million years or so. And yeah. And so we were also interested in determining whether we saw any differences when looking when making these analyses at different redshift intervals. So for instance, I have the same star formation history I showed before, but this time instead of separating into bursty and non-bursty regimes, I separated into different time bins corresponding to different redshift intervals. And I produced multiple panel plots like these, but in order to not give you guys a headache with so many panels, I would only focus on like 3 random ones. The redshift intervals here do not mean anything, they're just at random. And I do the same analysis. And when I do the same analysis, I find that I am again seeing this minimum scatter between at an average time scale of about 4 million years or so. And when I look at FUV, I see this about a similar trend as previously when looking at bursty and non-bursty regime. So in conclusion, I would like to leave you guys with the takeaway is that it doesn't matter whether I'm analyzing these bursty or non-bursty star formation regimes, and when analyzing these effective timescales, and it doesn't matter if there's whether the mass of the galaxy varies or different redshift intervals. I'm getting the same effective timescales, and I guess takeaway is that initially these indicators have a maximum timescale of about 10 million years or so for H-alpha, and FUV about 100. And I'm finding that the effective timescales, so when the emission is probing the emission at better, it's around 4 to 5 million years and 10 to 15 for FUV. So thank you.
Thank you.
Yeah.
Right, so when you convert from SFR in the simulations to live, you need to make some model assumptions instead of population modeling. That when you recover then with some measurements, some kind of circular reasoning, right? So you are comparing some SFR that you get from live, but you are assuming some modeling there, because in the simulation you get the SFR. So how is the assumptions that you get on the modeling influence your results?
Yes, so the indicator models, they're derived using a stellar synthesis model, right? And for H alpha, for instance, it is assumed that the star formation rate is proportional to the amount of ionizing photons. And for FUV, the calculations for the flux calculations from the stellar continuum is calculated similarly to as the flux calculated through a Galax FUV filter. So I don't know if that answers it.
Daniel?
So this great talk. That's a really interesting at reionization times when everything happens on very short time scale. Have you checked there is any dependency with the duration of the burst? So for a much shorter burst, is the time scale different?
I have not, yeah, but
Because that's what we see at high redshift, that there are very short time scales
okay.
for burst.
Thank you.
Have you looked at galaxies that are in the process of quenching?
Not necessarily, because the ones I've analyzed, they've all experienced these burstier, like time-steady star SFR. No, so in the future, I would like to play around with this and make like these toy SFRs to see if I get similar trends. So, yeah.
The results that you have suggest that the estimates we've made in the past was too high, and therefore at the time scale of, let's say, 100 million years, is it possible that maybe the NUV turns out to be more characteristic of that time scale? Have you been able to push your results to longer wavelengths?
Yeah, so I believe the NUV works at a time scale of about 200 million years or so. Well, this is FUV, right? So what I'm saying, I guess, here is that at these average time scales is when I get the most emission from whichever band I'm looking at. Not necessarily that, yeah, these are totally wrong, and I'm not trying to say that, but yeah, I guess for the other indicators, it would be really interesting. Yeah. Yeah.
So let's thank all the speakers of this morning again.